tells us something, about the structure of matter. And then later on, addressing a Royal Society anniversary meeting, he commented very prophetically that it would be really interesting to have, of great scientific interest, if it were possible in experiments to have a supply of electrons, of which the individual energy of motion is greater even than that of the alpha particle. So that was, he was prophetic in this statement, in that he kind of predicted other experiments that were vital to the exploration of the nucleon and nuclei structure. And those experiments were done in the 50s by series of measurements by Hofstetter. And this is where he took the electrons and he scattered of nuclei. He determined the charge and shape of nuclei and measured the finite size of protons. So this is a setup of his experiment. He used energy of electrons, 188 MeV. Here is an electron beam coming into the target. And then he had this spectrometer, and then he observed the scattering of the particles. And this is the result of the experiment as a function of the laboratory angle of scattering. And there are a variety of curves, but the data do not fit any of the curves. This curve is an experimental curve. And that that was the discovery of the fact, that led to the discovery that the proton actually had to have a finite size, which is of the order of 0.8 Fermi or so. So this is really the first experiment that measured the finite size of protons, that indicated the proton is not a point-like particle, but rather might have a structure. That structure was further explored in late 60s in experiment MIT and SLAC, which observed the highly inelastic electron-proton scattering. So what the Hofstetter did was an elastic scattering. Here they did an inelastic scattering. It was with much higher energy electron beam, 20 GeV electron beam scattering of protons. And the experiment, when compared to the prediction, which is here, the elastic EP scattering, and the experiment are the data as a function of the momentum transfer of the photon. This Q square is a very important variable. It characterizes the resolving power of the interaction, the form momentum of this photon. The data essentially spectacularly disagree with the prediction, as you might see, indicating that something else is going on, and that something else was really interpreted as a scattering of some smaller constituents of inside the proton. So here we have an electron. It's kind of a half of a Feynman diagram cartoon, if you wish. You have an electron scattering, coming in, going out, exchanging a photon, and scattering of the quark. And this variable Q square is very important. It tells us something about the strength of the, so to say, our microscope, if you wish to describe it like that. So I need to show this famous diagram. This is the diagram of this deep inelastic scattering of electron of a proton. The way to read it, to interpret it, is we have an electron coming in, and then we have a proton coming in, here represented as simply as consisting of some three components, three partons, although as we will see, the story is much more complicated. And then it interacts electromagnetically. So the electron interacts with one of those constituents and gives it a momentum transfer, and then the proton breaks up. And there are two variables that are very important for the further discussion. One I already mentioned, this is Q square, which is the minus virtuality squared of this exchange photon. And you can think of that, the higher Q square, the better resolution of your experiment. And the other one is X, is Bjorken X, which essentially has an interpretation of the longitudinal momentum fraction of the proton carried by the struck quark. So this quark interacts through electromagnetically with an electron, and it carries some momentum fraction of this proton. And that X variable which is constructed out of the Lorentz invariance, has the interpretation of the momentum fraction. And so these two variables are very important for the further discussion. Now, so the interpretation of the Slug-MIT experiments was that the deep inelastic scattering of leptons of protons, the reaction where the proton breaks up, can be thought of scattering of individual constituents of proton, which are partons or quarks. Parton is a sort of name that is usually used in the context of scattering here, but here these partons are of course quarks. And so what these experiments showed, this is the result of the measurement. So they measure the cross section as a function of this variable X, and if the proton would consist of 3 quarks, and let's say they would not interact, you could think that each of them carries 1/3 of the momentum of the proton. So you would see a delta function essentially at the position of 1/3. Now, if these partons interact with each other, let's say there are 3 of them, but they interact, they can share the momentum, then you would see some spread distribution. And so roughly speaking, this is what you see. So the measured cross-section, the observable that you measured in experiment, is directly related to now the distribution of the partons inside the proton, their momentum distribution. Like they share the momentum, you measure this distribution through that experiment. Now, the experiments didn't stop there. The next generation experiment with even higher energy was at DAISY. This was a Hera collider operating between 1992 and 2007. This was the only electron-positron proton collider ever built. Here you see the ring and 2 experiments where the electrons and protons were collided with each other. And the center of mass energy was 320 GeV. If you convert it to, you go to the frame on in which the proton is fixed, that is 50 TeV electron beam, so about 2,500 times more than at SLAC. So it was much higher energy, but the principle was the same. So to use the small electrons to look into the proton, but with a higher energy. And what was discovered was quite striking in that on the left, you see the old results, so from the lower energy experiments, and the right, you see the higher energy, the results from the higher energy experiments. And you see that essentially what is this result here on the left panel is what, roughly speaking, constitutes this measurement here, because as a function, again, of this momentum fraction X, which actually the higher energy is available at the experiment, the smaller X can be probed. So the higher energy experiment, Hera, could go into this low X region. And what was found was this rise, that the cross-section suddenly starts to increase very rapidly whenever the resolution is increased, this Q square, or with decreasing X. And so the natural question then arises, where does it come from? What is responsible for this type of behavior of the cross-section? And the answer is, it's quantum chromodynamics, is a QCD radiation. So let me try to explain what happens on the level of these diagrams. So first we have a simple scattering of electron and a quark coming with some momentum, and they interact elastically, essentially like billiard balls, and they scatter through the exchange of photon. But then this quark is charged, and it has both electromagnetic charge, but it also has a color charge because it's strongly interacting, and color is the charge of strong interactions, and it can radiate gluons. Like in electrodynamics, it would radiate photons, but it can radiate gluons, and therefore it can change its momentum. Because the coupling is strong, there can be many more interactions, so it can radiate more and more gluons. So this would be like in electrodynamics. Also, what it can do, it can essentially fluctuate into other quark-antiquark pairs. So if one imagines the proton as consisting of, let's say, 3 quarks, that is a naive picture. There are quantum fluctuations, and essentially through this experiment, one can resolve those quantum fluctuations. That again is something very similar to what would happen in electrodynamics. However, there are new components in strong interactions in that these gluons, the carriers of strong force, can split and interact with themselves because they themselves carry a strong charge. And so there are new possibilities or combinations of interactions that are in strong interactions, namely the splitting and recombination of gluons, which lead rise to the, let's say, more and more of these gluons, more and more of the carriers of the strong force as we increase the energy. So these type of processes are electrodynamics-like. They would occur in electrodynamics, except for, let's say, some overall coefficients. But this one is really unique to quantum chromodynamics, unique to the strong force. And so whenever this deep inelastic scattering process occurs, one is not really probing some what we call valence quarks, but we also probe these quantum fluctuations that arise through this complicated dynamics. So there can be a lot of these emissions in this process, which somehow have to be taken into account and described. So what I said, what I would like to summarize it. In electrodynamics, we have electrons and positrons, which have electric charge and interact with photons through photons, which themselves are not charged. On the other hand, in quantum chromodynamics, we have quarks and gluons, which are charged. And gluons, unlike photons, do have charge, so there is more dynamics involved because they can screen, they can split, and they can recombine. Now, this looks very complicated, and so the question is there a way to describe it? And I want to just introduce this concept of parton evolution equations because they are in some sense related to the name of Parisi, who obtained a Nobel Prize. So I would just like to spend 1 minute on that. And this complicated radiation, in some approximation, can be resummed. So when we think about probing the proton at smaller resolution and at higher resolution, it's a very complex system. However, there are some things which can be calculated from first principles, and using the methods of perturbative expansion, one can essentially predict the change between the process in which the photon has, let's say, low resolution and the process in which the photon has high resolution by appropriate resummation in some approximations. So we cannot predict the completely say what is the structure of the proton from first principles. There are numerical methods that can go up to some point. But what can be done is a calculation of the change with respect to the scale, the resolution scale. And this is done through what is called the parton evolution equations, which predict this change. It can be calculated and it changes on what we call the parton density. So now we don't think about the proton as essentially consisting of fixed number of quarks. We can think of the proton as having gluon and quark distributions that are evaluated as there are functions of resolution scale and the longitudinal momentum fraction. So we can think of entire distributions of quarks and gluons, which we can on one hand measure, and on the other hand try to compute from first principles in QCD. So these equations that give us some information about these parton densities are called Dokshizer-Gribov-Lipadov-Altarelli-Parisi equations. And Parisi was one of the authors, and this is the famous paper, Asymptotic Freedom and Parton Language, where these equations were proposed. And he got a Nobel Prize recently, among other things, for that a very important contribution. So coming back to the picture, what comes out of the experiment and how we can interpret it. So the high energy experiment of electron-proton scattering results in this measurement where we see the cross-section that suddenly is increasing with both the resolution scale and this momentum fraction. And that can be related to these parton densities, to the densities of both quarks and gluons, which undergo certain dynamical evolution, and the rise, their increase with this parameter x is what is responsible for the rise of the cross-section. So let me maybe describe in more details what is shown on this plot. These are these parton densities for quarks and gluons, and you see two functions that have such maxima, and they correspond to what we call the valence quarks. So if the proton, let's say, would consist only of these three valence quarks, three quarks, and there wouldn't be this all sea of other quarks and gluons, these would be the distributions of it, roughly speaking, three quarks interacting with each other. But there is much more. There are gluons and C quarks, and what you see on this plot is that they are here multiplied by 0.05 because they are so much higher, so much larger than these valence quarks, particularly in this small x region. So the proton, rather than looking sort of like naively consisting of three quarks, is really a very, very complex system, which can be explored very cleanly in these electron-proton experiments. And when you go to higher energy, then you're even exploring more and more this region of small x. So just to summarize this part is that at low energy, we kind of think maybe these are, three quarks interacting through a complicated field, but at high energy, what we see is an emerging picture which is far more complex, with the whole distributions of quarks and gluons. Which brings me to sort of the next topic or related topic, is that on one hand, we see this complexity of the proton as explored in these experiments. And on the other hand, we know that these quarks and gluons are actually forever confined in these hadrons. So let me go over, and I hope there are students, because this is a slide for students, is that the strong force is extremely, extremely strange in that we think of these two quarks, which are connected by a color string, which is this gluon field. And what happens is that as the string is stretched, this force increases. And at some point, you cannot really they cannot be pulled apart indefinitely. But at some point, there's so much energy in this string that essentially two other quarks are coming out of vacuum. And essentially, we have a system then interact of let's say, quarks, anti-quarks, quarks, anti-quarks. So there are two new quarks being produced. And these quarks always come in what we call the colorless objects, the colorless hadrons, protons, neutrons, and mesons. Nobody ever managed to observe the single quark or gluon. So the color is confined. So there is this complex structure is confined inside hadrons. And then when we try to pull apart, then what happens is that new hadrons are produced. This process is very complicated. It's called hadronization. It's not very well understood. It can be modeled. And so in that sense, the quarks are confined inside the hadrons. On the other hand, when we explore and when we look with these experiments, as I was describing, electrons looking inside the protons with ever higher resolution, we see that when quarks are very close together, they interact very weakly. So the interaction is weak at very small distances. This is what is referred to as asymptotic freedom. So to summarize, the QCD has this very strange behavior in which there is confinement at small momenta or large distances. The interaction is strong, and the dynamics is very difficult to solve only through essentially numerical methods. Here you see, for example, the potential numerical simulation of the quark-antiquark potential using lattice simulations. And this potential tends to be linear at large distances. So there is confinement. Quarks cannot really be seen as isolated entities. They are confined in mesons or baryons. On the other hand, there is asymptotic freedom. So when the structure of protons is tested at a very, very small distances, at large momenta, the interaction is weak. And this is where we can solve the theory by using perturbative methods, that is expansions and powers of coupling. So here is an example from another experiment where we have, for example, two protons colliding at the LHC, and quarks are interacting at very short distances, that they get very, very high momentum and they are knocked out. What happens is that we can see in the experiment the remnants of this interaction in the form of jets. So kind of the jets trace the paths of these quarks. But of course, the quarks themselves are not observed because later on they turn into hadrons. So there is both, in the observation of this process, there is both asymptotic freedom and confinement at work. And finally, this can be illustrated by looking at the coupling between the quark and the gluon as a function of the scale, of the renormalization scale. And the measurements clearly indicate that this coupling has exactly this behavior. So here the coupling tends to be small. If we go to higher and higher scales, very, very small distances, that's the asymptotic freedom. And it becomes larger and larger once we go to smaller scales, smaller momenta scales, and larger distances. Also note that the value of this coupling constant is fairly large if you compare it with QED coupling, which is much smaller. This is why it shows the strength of the strong interactions. So in this second part of the talk, I would like to go into the future. So we've seen that electron-proton experiments are really the cleanest experiments to explore the nucleon and nuclei structure, as well as several aspects of strong interactions. So the question is, what is the future? And the future is in electron-ion collider that is being planned in the US, and this is sort of the artist depiction of the scatterings that are going to be explored in this experiment. So here we have a nucleus, And then we have electron beam, which is polarized, interacting with these quarks and gluon inside. So I already mentioned the EP collider at Hera, which was a fantastic machine and provided a lot of information about the physics that I have briefly described, the structure functions, parton density functions. It did establish the growth of the gluon density with decreasing X. It did the measurement of coupling constant and provided a very important input to Large Hadron Collider. But it had some limitations, let's say, in that it had limited statistics, it didn't have nuclei, and it didn't have polarization. So the electron-ion collider is meant to fill in that gap. And so the electron-ion collider is the project that is being proposed to be installed in Brookhaven National Laboratory. So here you have a New York City. And there is an existing RIC complex at the Brookhaven National Laboratory, which collides, there is a hadronic ring. And there will be an upgrade to add the electron complex. This is a picture of the proposed complex. And what this collider will have, so it's going to collide electrons with nucleon and nuclei beams. And it's going to have polarization, so you can polarize both electrons and protons. It's going to have a wide range of nuclei, from deuterons to the heaviest nuclei, gold, lead, or uranium. It's going to have slightly lower energy than Hera. However, it will have variable center of mass energy, so that is also a very big advantage. And it's going to have high luminosity, which of course means that it's going to have high statistics and therefore high precision. So a few things, if I'm going to only list a few questions that this collider can address. If you're interested, there is a yellow report, a big document, which was released at the beginning of this year. It's on archive. And there are a number of the variety of processes that are being described that will be measured by in this machine. So some physics questions that are going to be explored at the electron-ion collider. So one is how these nucleonic properties like mass and spin of protons and neutrons emerge actually from partons and their underlying interactions. So I showed you how complex the proton is, but then it has spin 1/2, it has mass. How does that emerge from these underlying constituents and the interaction? So that's one of the questions. How are these partons distributed in position space? We know a lot about their average distributions, but we know much less about spatial distributions of partons inside the proton. And this is one of the big questions that this machine is going to address. What happens if the quarks, which are knocked out of the protons, then go through a cold nuclear medium? How do they interact? This is one of the big questions, and this is also very important in the context of LHC. The other thing is how the hadronization happens. How these quarks and gluons, when they are knocked out, how do they hadronize? And what happens with hadronization when passing, for example, through a heavy nucleus, through some environment? Finally, how these quark-gluon interactions create the nuclear binding, how they are modified. There are a lot of questions that we still don't know. And finally, there is a prediction that when you go to very, very high energies and in heavy nuclei, the quarks and gluons, because they are rising towards the small x, and in heavy nuclei there is more of them, they can start to saturate. And there is a novel sort of regime of QCD. That's at least the prediction. So EIC with its precise measurements can test all these, explore all these questions. So let me start with really few selected questions that EIC will try to address. And one of them is, what is the origin of the mass? So this is a standard model of particle physics, leptons, quarks, and bosons. And we know that they have mass, except for a photon and a gluon. And there is a Higgs boson, and we know very well from LHC that the Higgs mechanism is responsible for the masses of WZ leptons and quarks. And we know that the generation of elementary masses proceeds through the interactions with the Higgs field. And this is one of the sort of the biggest discovery of LHC, is the discovery of the Higgs boson, which is the excitation of this field. And here you have the measurement of the coupling of the Higgs versus mass, which agrees fantastically with the predictions. And so we know that the masses of the elementary particles are generated with the Higgs field, but that is not enough to tell us about the mass of the proton, because the mass of the proton is very heavy, 938 or so mega electron volts. But then if you take the masses of quarks in the proton, they add up maybe to 10 MeV or so. So the masses of individual quarks do not add up to the mass of the proton. And the Higgs mechanism, therefore, is not a dominant mechanism for the generation of the mass of the proton. And so the 99% of the mass, visible mass, and I underline the word visible mass of the universe, is actually generated by the strong force, by QCD interaction. And so this is one of the questions that can be explored at the IC, how does it happen? Or what is if we take the masses of some, not necessarily protons, but some other particles, how the Higgs mechanism generates the mass, and what is the percentage of the strong force generating mass? So one of the examples of how this can be explored at the IC is, for example, looking at particles called pions, the mesons that valence structure have of U and D bar quarks, and kaons, which have also the strange quarks. And the difference between the two systems is that the strange quark is heavier, so the Higgs mechanism is contributing more to the mass of the kaon. So in some sense, we can compare the pion and kaon structure functions and different form factors in a very wide range of scales and learn something about the mass generation in one system and mass generation in the other system. The other process that is going to be explored in the context of mass generation in EIC are precise measurements of the J-psi production in EP, particularly the so-called threshold production. So mass generation is one of those critical questions that can be more explored with EIC. The other question that will be explored at the EIC, because it will have polarized beams, is spin. Now, we know that spin is a fundamental quantum property of particles. It's kind of an intrinsic angular momentum. It's a quantum property. And we know that protons have spin 1/2, quarks also have spin 1/2. So then one can ask, well, how does the spin emerge of the proton? And one could imagine, well, we have a proton, it has a spin 1/2. It has these three quarks, three valence quarks. They also have spin 1/2. So maybe the picture is that it comes from the spin of quarks, right? We will put two quarks spins parallel, one quark spin anti-parallel, problem solved. is it? Well, it turns out not so fast. There were experiments done in late 80s, and I put this abstract, well, this page from this paper here because you can recognize certainly some names that are very familiar here. So this was a very important experiment, and what it showed was that actually the spin of the proton doesn't necessarily come from this naive counting of spin of the quarks. So what this experiment did, it was a polarized muon proton scattering. So here these arrows indicate the polarization, the orientation of spins. So in one scattering, the spins were parallel, in the other one were anti-parallel, and one can measure the asymmetry, so the difference between the cross sections when they are parallel spins and anti-parallel orientations. One can divide it by the sum, this can be measurement, and one can infer how much spin is actually in quarks by observing the scattered particles. And the result, and this is the direct quotation from the paper, said that in addition, the result implies that in the scaling limit, a rather small fraction of the spin of the proton is carried by the spin of the quarks. So this is very interesting. So the question is where the spin comes from of the proton. And Jaffe and Manohar and G in 90s proposed that there may be different contributions since it's such a complex structure. The emergent spin is not only come from these quarks, but also can come from gluons, and also can come from the orbital angular momentum of quarks and gluons. If this is such a complex dynamical system, they will have some orbital angular momentum. And so one of the goals of the EIC with its precision and polarized beams is to figure out this decomposition by measuring what we call the quark helicity, also the gluon helicity, and then maybe infer and constrain the amount of orbital angular momentum of quarks and gluons. So this is one of the other very big questions that EIC will be able to explore. Now, the next thing next question that can be explored at EIC is what is called the nucleon tomography. So I spent quite a bit of time at the beginning by telling you about these parton distributions and how they tell us what they tell us about the density of these partons of quarks and gluons inside the proton, but they are very integrated. They only tell us about the distribution in longitudinal momentum. But what about the spatial distribution? How they are spatially distributed? Are quarks and gluons distributed in the same way? Are there fluctuations? We don't know much, and by performing some experiments, some processes measuring some processes at the EIC, we will be able to explore that. So if you remember at the very beginning, I mentioned that Hofstetter measured the shape and size of nuclei, the charge distribution, through elastic electron nucleus scattering. So one can measure also the partonic distributions by looking at processes that are almost elastic. They are somewhat different than completely elastic. They are called diffractive events. So what is diffraction? In optics or in general physics, we know what is diffraction, right? For example, here we have diffraction of water waves passing through the small entrance. There's some small entrance and we see diffracted waves. Now, diffraction is very useful because if you look, for example, at diffraction of light and you have certain aperture, you can immediately see what was you can infer from the image what was the shape of the aperture. So here, the circular aperture, here, this is diffractive image of rectangular aperture. And the diffraction pattern, far away from the obstacle, is essentially a Fourier transform of the aperture field. So by measuring the diffraction and Fourier transforming it, you can tell something about the structure of the obstacle or the opening in your experiment. And moreover, it's a very good experiment because it's not only that you can measure whether it's circular or some simple shapes, you can actually explore very complex structure, as is illustrated in this probably most famous X-ray photo, right? So this is a Gosling-Franklin photograph, X-ray diffraction, which includes enormous amount of information that allowed Watson and Crick to model the double helix, because by measuring, for example, the angle between these two axes, it tells us about the pitch of the helix. Measurement of the intensity of these lights tells us about that this is double helix, etc. So there is enormous amount of information, very detailed information that can tell us about complex structure of an object. One thing, though, that is essential for this to work is that the object itself cannot be destroyed in this process. If the light would be so intense that it would destroy the object, then you don't have diffractive pattern. So what is diffraction in hadronic and nuclear physics? Well, in quantum physics, it's a propagation and interaction of particles as an absorption of various components of the wave function. And in electron and hadron or nucleus scattering, like in EIC, you have this electron and proton coming in, and normally, or most of the time, the proton is fragmented. So the electron scatters, the proton breaks up, and then there is something produced in the central detector. Now, diffractive event is an event where the proton stays intact. So electron scatters, proton stays intact, and something else is produced in the central region, separated from this proton. This is a diffractive event. So it's more complicated than purely elastic event, where you would have electron and a proton final state. You have something else also in addition in the central region. And it turns out that these type of processes are actually quite common. For example, at Hera, 10% processes were diffractive. So that's very interesting. And these processes can provide a lot of information about the structure. They are not very easy to describe, because one needs to describe how is it that proton stays intact, and this is intrinsically a non-perturbative process, but they are very useful. And for example, one process that can be used to map the gluon distribution, the spatial distribution inside the proton, is when you have this diffractive production of particles of J psi. And so you take electron and a proton are scattered, and then there is J psi being produced, which decays, and nothing else in the detector. And this process, because the proton is intact and the way J psi is produced, is very sensitive to the shape of the gluon distribution. So here you see the simulation that, so these are simulated data. Again, this is a cross-section as a function of the momentum transfer, which you can think of scattering angle of the scattered proton. And what you have below is essentially extracted spatial distribution of gluon density in the proton by Fourier transform. So it's like here you have a diffractive image of the DNA, and here below you have a DNA itself. So what is the distribution? But here, of course, it's a spatial distribution of gluons in the proton. So this is another important process that will be measured in EIC, and one of the advantages of this accelerator over previous ones is that it's going to have dedicated instrumentation that will allow to catch this scattered proton. And finally, the other aspects that will be, or questions that will be asked at EIC is the nuclear structure. So I spend a lot of time talking about quarks and gluon distributions inside the proton. But now what happens if this free proton is not free, but it's bound inside the nucleus? Well, how this structure gets modified. And so that can be also explored by electron nucleus scattering. And here EIC will really be very, very useful. So typically this nuclear structure is measured or tested by forming what one calls nuclear ratios. So one performs a measurement of some observable on nucleus and then divides it by the measurement on the proton scaled by, in this case, by mass number. And whenever the ratio is different than 1, then we are talking about nuclear effects. So typically, this is a typical ratio, nuclear ratio, the structure function here for iron divided by the deuteron is a function of x. And you see it's a very, very complicated function. And EIC will make a big progress in understanding this in measurement of these structure functions, because it goes into the kinematic range, which was never really previously explored by any other deep inelastic scattering measurements. Here you have an example of the, in some sense, ignorance or current ignorance. In other words, this is the ratio of the parton densities. So ratio of the parton density in the nucleus divided by the ratio in the proton. And if you focus on this right panel, you see that there is this shaded kind of gray-green area. This is the uncertainty. So the uncertainties in these ratios, in a lot of these ratios, are currently of the order of 100%, because there are no precise data that test this region on nuclei. And EIC will be able to fill in this gap. Here we have an example of the simulation. So for example, this is a relative uncertainty of this gluon distribution in the nucleus before and after including EIC. So anything that is blue band is before EIC, and this orange, which is essentially shrinking uncertainty, is when you include, in this case, simulated EIC data. So shrinking of the uncertainties of the parton distribution is in nuclei. This is what's going to be possible at this collider. And finally, I mentioned one more let's say, a prediction that is going to be tested at the EIC, and namely something called the saturation of partons in nuclei. So I showed you that there is a change of the parton distribution as a function of the resolution and as a function of the energy. There is also change as a function of the mass number. And there is a prediction that at some point, here you go to higher energy or the smaller x. At some point, this density of gluons is so high that novel phenomena will occur. Namely, these gluons will start to interact with each other. And there will be some characteristic scale, which is a function of momentum fraction as well as mass number, where the dynamics will change. And for example, one will have to change or modify all these parton evolution equations, which will no longer obey the equations that Parisi has derived, but they will contain also some nonlinear terms. So we don't know where exactly this is going to happen and for which value of mass number A, but the EIC can test this prediction in nuclei very precisely. So I'm coming to an end. So my summary, in the summary, the strong interaction is one of the four fundamental forces in nature. It's the strongest of all. Quantum chromodynamics is a quantum theory which describes the interaction of quarks and gluons and has a color charge. It's a very complex interaction. There are many emergent phenomena like hadrons and confinement of color. And proton has a very rich structure, which is best explored in these electron-proton interactions. The next generation collider, EIC, electron-ion collider, is a unique facility where we will explore the high-precision nucleon and nuclear structure. And there are a number of questions which will be addressed. It will measure proton and nuclear structure functions and these parton density functions. It will perform tomography, so map the spatial distribution of quarks and gluons. It will address the questions of spin, emergence of spin in proton, possibly high density or saturation phenomena in nuclei, diffraction, which is related also to this nucleon tomography, and also something that I didn't have time to talk about. It will explore also what happens if quarks and gluons travel through the cold nuclear matter. So thank you for your attention. Well, let me post this one. Wesołych świąt.
Thank you, Prof. Staśto, for a beautiful lecture. Those who would like to ask a question, they are asked to raise a hand. I can see hand of Prof. Jerzy Pniewski. So, yes, please. Can you? Yes, yes. We can hear you. Yes.
Okay. Thank you very much. Thank you for a very nice presentation, and I have just a small comment, because you mentioned Hera and you somehow compared the new project to the Hera achievements, and you mentioned also that there was no polarization in Hera, if I understood correctly. This is not true. There was no polarization in Hera 1, but in Hera 2, both electron and positron beams were polarized. And so we did have a lot of polarized data. They were combined in most analysis of the proton structure, but there were some interesting studies done, including the polarization information, for example, on electroweak interactions and
yes.
searches. So there was this option.
Right? Sure. Yeah, yes, I was. Thank you very much for that. Of course, in some sense, I should have been more precise in terms of no polarization of proton beams, right? So in that context, yes. So the Hera had this polarization, which was then for electrons and positrons, and as you mentioned, there were electroweak data there. But here we are talking about more. There is more here, of course, in terms of because Rick has these Siberian snakes, which allow for the polarization of the proton target and lighter nuclei, right? So yeah, but you're absolutely right. Yes.
Okay. I can see that the next question. Please, Professor Iwo Bielski-Biudla, please go ahead.
I wonder why neutrons were not mentioned. When you divided nucleus by protons, you did not mention neutrons, that they also contain charged quarks. Are they negative?
Sure. Of course. So what? Of course, the neutron structure is going to also be measured and has been measured. For example, by looking at deuterons, and there are dedicated measurements in which, for example, one does the proton tagging. So, for example, one can have a deep inelastic scattering, and then the tagging of one of the spectators, And in that way, one can measure the neutron structure as well. So of course, that is also is and will be explored.
Thank you.
Okay, I can see the next question. Please, Professor Tomasz Matulewicz, please ask a question.
Yes, I have a question concerning the case of the mass change of charged kaons. This is a hot topic in low energy nucleus collisions around the production threshold. You meant that the mass of kaons would be influenced by the Higgs field. What was exactly the point?
Well, the point was that okay, so how they are going to explore the mass generation mechanism, and I think there are at least two ways to do it at EIC, and one is the threshold production of the J psi, where there will be a contribution to the trace anomaly, and the other one is by essentially, I think, comparing the form factors and comparing the structure functions and their scale dependence of pions and kaons, because the kaons kaons have strange quarks. So in a sense, the Higgs field contribution there is larger than, or is different than in the pions. So essentially, by comparison, the pions and kaons and the structure function, the scale dependence. So this is one of the ways, and the other one is, as I mentioned, the J psi and maybe upsilon threshold production.
Thank you.
Please, Basio, go ahead.
Well, as a comment, I would like to add here the fact that our guest today is very deeply and with great success involved in the proton structure theoretical research, and also in preparing the background for the new machine EIC. So, well, we should realize this and may ask her all sorts of questions concerning this new device, which hopefully will soon be operational, soon on the scale of large machines, of course. So that's
right?
8 to 10 years, but that is still soon.
So, right.
Thank you.
Jan Kalinowski.
So I have the question concerning the EIC. What kind of ions can be accelerated in this ring? A broad range of ions, or just?
Yes, pretty much, anything from neutrons to uranium. What exactly will be accelerated, that of course is going to be the question in terms of time and type of interest, but pretty much very range of, yeah.
In principle, there is no restriction on what kind of ions you can have, yes?
I think there is no.
Okay, thank you.
Basio, are you going to add? No. Are there any other questions or comments? Yes, there is a student, T. Han Lee. Please, your turn. T. Han Lee, are you going to ask a question? Because you raised your hand. Okay, if not,
He may be muted. He is muted.
he's muted, but he can unmute in principle. So maybe
you can also do it for him.
yes. I want to allow.
Oh, but there comes a chat. Can you allow me to speak? So you have to unmute him.
Yeah,
yes. Can you now unmute? Okay.
Yeah.
Thank you for nice talk. I wonder, is there any actually possibility to see nuclear structure not from the collider, some sort of interference experiment or something like this? Because we if we want to more and more precise like the structure of the elementary particle, you have to increase actually more and more actually energy. So so we have actually limited energy source. So I wonder, is there any other way to see inside the nucleus? I mean, like interference pattern or some diffraction or some other indirect way to probe nuclear structure?
Yeah, so that's a very good question, right? Because we have, I mean, in some sense, we have limitations of the energy, at least on the accelerator side. Although, you know, in some sense, we don't have, well, we can go around this limitation, for example, by, one can go to higher energies by using, let's say, high energy neutrinos, except that then you don't have this precision. It's more of an input rather than the output. In some sense, what you're asking, I was trying to address here by looking at more rare processes, right? So all kinds of diffractive processes where you can explore the nuclear structure, right? But you're right, at some point we have limitations in terms of energies that can only be circumvented, you know, maybe by using some information from astroparticle, but I don't have a better answer here, to be honest.
I can see a question from Professor Michał Bai.
Well, I'm not a high energy physicist, so probably my question will be very naive. The question concerns the spin of proton. You say that the spins of quarks are only partially responsible for the spin of proton. Does it mean that if you sum up 3 spins which are 1/2, you do not get 1/2?
Well, it's more complicated than that, in a sense that I had here, maybe I can bring this, although yes, so maybe I can share the screen. Okay, can you see this or not?
Yeah,
okay.
we see it.
Yeah. Okay. So this is the this is the slide. Okay. So what I meant is, what one is looking at is really one has to look at this quantity, and this is what is called the quark helicity, where there is an integral over the essentially the fraction of the longitudinal momenta of different distribution of quarks that essentially give rise to the spin. And this is, well, at best 30%. So this doesn't add up. So it's more complicated. One has to really go through this integral, which indeed doesn't add up to 1 or 1/2 proton spin. So it's in terms of these quantities that are called the quark helicities, or the distributions of so these are differences between the quark, measured quarks, which have parallel and anti-parallel orientation. So when you look at this quantity, it is indeed not summing up to the total proton spin. You have to add these distributions from gluons, and what is left is going to be the orbital angular momentum. I don't know if I answered your question correctly. I mean, precisely, it's you cannot really think of them as static objects, right? that you have to think about them as distributions here.
Yes, are there any further questions? Maybe comments? Barbara Badek, please go ahead.
Yeah, to add to the previous question and comment, maybe one can view it like this, that those distributions seen here on the slide, delta U, delta anti-U, and so on, these are probability functions to find certain helicity for a quark which carries certain momentum fraction x, like this. And then we integrate those probability functions. So as Anna just said, these are not static quantities. There is certain dynamics in it.
Thank you. Yes, thank you for this comment. Yes, if there are no more comments, let me thank Professor Anna Staśto for visiting us and for patience to us. And let's say that we are sorry for the perturbations from the previous week and for today. And you're all welcome to the next colloquium that will be held in the middle of January, on 17th of January. So taking opportunity, I wish you all quiet and good time of Christmas, and hope to see you in the next year. So in the name of those who co-organized this colloquium, so Professor Badewek, Jan Kalinowski, Jan Chwedeńczuk, we wish you all the best for the new year. Thank you, and see you the next year.
Thank you very much. Thank you.
Thank you. Bye.
Thank you. Goodbye.
Goodbye. Goodbye. Thank you. I'm finishing recording.